This has a self-indicating colour change, and when we see the colour change, we can answer the question, how much has been oxidised? In this video, I'm going to go over the method, and then I am going to go over lots of calculations for you. I'm going to do this really slowly, step by step. You can skip through the slow bits if you don't want to watch them. The important thing to remember when you're working out equations is that the manganate ions are going to be reduced. You're going to have your potassium permanganate in your burette, and then your known volume of the solution that we are analysing goes into your conical flask. This needs to be done in an excess of acid, and this is going to be to provide the hydrogen ions that are needed for the reaction to take place. We do not need a separate indicator for this, as the potassium permanganate decolorizes as it reacts. We know we've reached the end point of the titration when we see the first permanent pink colour. This will happen when the potassium permanganate is in excess. As with all titrations, we need to be working towards concordant titers. Because of the gorgeous deep purple colour of the potassium permanganate, it's really hard to see the bottom of the meniscus. So for these titrations, we read it from the top of the meniscus. If you do this consistency, the difference between the top and the top, then you will still get the actual titers. Here is our first question. And what I'm going to do is break it down for you, and then I'm going to show you how to answer it. So I always like to have a little list of the important bits over to one side, so that when I'm answering the question, all the information I need is in one place, as opposed to having to go back through the question to answer, to look for all the information again. So 25 centimetres cubed of hydrogen peroxide was made up to 250 centimetres cubed with water, and from this solution 25 centimetres cubed was taken. So we need that for later. There's been a dilution going on. This 25 centimetres cubed was titrated against 23.45 centimetres cubed of 0.0200 moles per decimetre cubed potassium permanganate. Calculate the concentration of the original solution of hydrogen peroxide in grams per decimetre cubed. So first of all, we are going to work out our equations. Now, this manganate equation is one that hopefully you'll be familiar with, and if you're not familiar with it already, you will be very, very shortly, because this comes up a lot. We have manganate being reduced to manganese 2 ions. We have oxygen on the left hand side. We need to add water on the right hand side to balance that out. Now we've added water on the right hand side, we need to add hydrogen ions on the left hand side and electrons on the left hand side to balance that out. If you are not familiar with these, I have a separate video taking you through how to balance these equations. Now we have hydrogen peroxide. This is going to be broken down into oxygen. To balance this out, we need to add hydrogens and electrons on the right hand side, and this is our oxidation reaction. To combine these into an overall reaction, we need to multiply the bottom one by 5 and the top one by 2. That way we have the same number of electrons on the left hand side and on the right hand side of the equation. Because in our redox reaction, the electrons have to go to and come from somewhere. They can't just disappear. The easiest way to do this, to make sure you don't make mistakes, is to write this out fully. I know it's very long, but the best way to do this to make sure you don't make mistakes is to write it out fully. Once you've got it written out fully, we can start cancelling things. So 10 electrons on both sides, they can be cancelled. 10 hydrogens on the right hand side will cancel out 10 of the 16 hydrogens on the left hand side. Now this looks a little bit messy, this equation, so I'm just going to tidy this up a little bit. Rubbing things out is very bad practice, so I do not want you to do that. I'm just doing it to make my life a little bit tidier and a little bit easier. I would like you to rewrite the whole thing out in full. Now we have our equation telling us what's going on. We can sort out the order of things that we're going to be doing. So we're going to work out the moles of manganate. We're going to use this to work out the moles of hydrogen peroxide. We're going to take that and work out the number of moles of hydrogen peroxide in the 250 centimetres cubed, and then we are going to remember the dilution that was made, and we are going to go back to our original solution and work out the concentration in grams per decimetre cubed. Moles of our manganate is going to be concentration times volume divided by 1,000, which is going to give us 4.69 times 10 to the minus 4 mole. We can go to our equation and see that they are in a 5:2 ratio. So we take our 5:2 as a fraction, or you can do it as a whole number. We times that by 4.69 times 10 to the minus 4, and that will give us the number of moles of hydrogen peroxide involved in the reaction. That gives us 1.1725 times 10 to the minus 3 mole. Now, we used 25 centimetres cubed from 250 centimetres cubed. So to get back to the 250 centimetres cubed, we need to times that by 10. So 10 times 1.1725 times 10 to the minus 3 will give us 1.1725 times 10 to the minus 2. Now we want our concentration to the original solution in grams per decimetre cubed. So to do this, we need to work out the mass of hydrogen peroxide. I remember there was an original dilution that went on. We had our 25 centimetres cubed made up to 250, and then from that 25 centimetres cubed was used in the dilution. So we take our moles of hydrogen peroxide, we times it by the MR so we can get it in grams, and then we need to get it in decimetres cubed. So we times it by 40 so we can go from the 25 centimetres cubed up to a decimetre, which will give us a final answer of 15.9 grams per decimetre cubed. Again, with this question, we are going to work through sorting out the numbers, and then we are going to do the calculation. So iron sulfate was made up in 250 centimetres cubed solution, and from this 25 centimetres cubed was titrated against 0.02 moles per decimetre cubed potassium manganate 7. The titre needed to oxidise the iron sulfate was 24.2 centimetres cubed. Calculate the original mass of the iron sulfate. First thing we need to do is work out our equations. Now these may be given to you in an exam, or you might have to work these out for yourself. We have our manganate being reduced to manganese 2. And remember, the only thing we can add to these is hydrogen ions, electrons and water. To balance out the 4 oxygens on the left-hand side, we need to add 4 waters on the right-hand side. To balance out the 4 waters on the right-hand side, we need to add 8 hydrogen ions on the left-hand side and 5 electrons to make sure the charges balance. Iron is going to be oxidised, so it's going to start as iron 2 and then get oxidised to iron 3. And for this, we just need to add on our electrons. Now we need to balance these to make an overall reaction, which just means we need to times the bottom one by 5. When you're balancing combining equations, you need to look at the number of electrons. My preference is for you to always write out everything in full so you don't forget things and you don't make mistakes. Then we can go back and cross things off afterwards. We're going to work out the moles of potassium permanganate used. From that, the moles of iron sulfate. From that, the moles of iron sulfate in 250 centimetres cubed. And then we're going to use that to work out the original mass. For our moles of potassium manganate, we can do concentration times volume, so 0.020 times 24.2 over 1,000 will give us 4.8 times 10 to the minus 4 moles. We can look at the ratio in the equation and see that for every 1 mole of manganate ions, we have 5 of iron. So we need to take the moles of potassium manganate and times that by 5 to get the moles of iron involved in the equation, giving us 2.4 times 10 to the minus 3 mole. Now we need to work out how much we had in 250 centimetres cubed. So we take the moles in 25 centimetres cubed and times that by 10. This just has the effect of changing it from 10 to the minus 3 to 10 to the minus 2 mole. To work out the original mass, which is what the question is asking us, mass is moles times mR. Moles, 2.4 times 10 to the minus 2 times 152, which is the mR of iron sulfate, which will give us 3.6 0.48 grams. A sample of iron ore was tested to determine the percentage of iron present. 3.68 grams of the sample was made up into 250 centimetres cubed solution. 25 centimetres cubed of this was titrated against 0.03 moles per decimetre cubed potassium permanganate, and it was found that 22.5 centimetres cubed of potassium permanganate was needed to fully oxidise the sample. Again, first thing I'm going to do is pull the numbers out and find out which bit I'm actually interested in. First thing we're going to do is to work out our equations. Hopefully you should be getting familiar with this equation by now. If you can't remember it for your exam, it is really worth knowing how to work it out. Hopefully you can start to see a pattern in the way that we are answering these questions. So to work out the moles of manganate, we're going to do the concentration times the volume over 1,000, which is going to give us 6.75 times 10 to the minus 4 mole. We can look at the equation and see that iron and manganate are in a 5-to-1 ratio. So we can take 6.75 times 10 to the minus 4 times it by 5, and we will get 3.375 times 10 to the minus 3. We need to take this back up to 250 centimetres cubed. So 3.375 times 10 to the minus 3 times 10 gives us 3.73 times 10 to the minus 2. Now we need to look at the percentage of iron in the original sample. So we need to find the mass of iron. So we take our moles, 3.375 times 10 to the minus 2, and multiply that by the MR, which means there will be 1.88 grams of iron in the original sample. The sample of iron ore that was tested was 3.68 grams. So 1.88 divided by 3.68 times 100 will give us 51.2%. 0.072 grams of sodium sulfite was made up of 100 centimetres cubed of solution. 25 centimetres cubed of this solution is titrated against 26.2 centimetres cubed of 0.02 moles per decimetre cubed potassium permanganate. Calculate the percentage purity of the original sample. And again, the first thing I'm doing is pulling out all the numbers from the question. The first thing we always need to do is to work out our equation. Hopefully the one for manganate is becoming very, very familiar by now. Our SO3 2- ions are going to be oxidised to SO4 2- ions. We treat this in exactly the same way we would balance any other ionic equation. And to balance them, we need to times the top one by 2 and the bottom one by 5. Now we've got the full overall equation, we can start to cross things out. And again, it's very bad practice to rub things out in an exam, but I'm just doing this to tidy it up a little bit for you. Now we have our equation, we can actually start working out the answer. For our moles of manganate, we can take the concentration 0.0200 times it by the volume 26.2 over 1,000, which will give us 5.24 times 10 to the minus 4 mole. These were in a 5-to-2 ratio in the equation that we worked out, so 5 over 2 times 5.24 times 10 to the minus 4 will give us 1.31 times 10 to the minus 3 moles of our sulfite iron. To get that into 100 centimetres cubed, we're going to need to times that by 4, giving us 5.24 times 10 to the minus 3 mole. To work out the mass of sodium sulfate, we need to take the moles, 5.24 times 10 to the minus 3, multiply it by the MR, 126.1, and then we are going to get 0.66 grams. Now do not use 0.66, use the whole number on your calculator, otherwise you're going to introduce a rounding error in this. So use the whole number on a calculator and then divide it by the 0.720 grams we got given in the original question. You'll get 91.8% purity. Slightly harder question now. We need to calculate the charge on some vanadium ions. Now, calculate as the command word means we need to use maths to prove it. You should know from the question. The question tells us a violet solution containing vanadium N plus ions was left. You should be able to recall from memory what charge a violet solution containing vanadium 2 plus ions. And if you don't, then I've made you a separate video with some super fun and interesting flashcards so you can learn them. Please learn your charges and your colours. It will make your life a lot easier. So hopefully you know the answer to this question already, but you're not going to get any marks just for writing down that you know what the answer is, because we have to calculate it and we have to use maths to prove it. I know it's very annoying, considering you already know what the answer is, that we have to go through quite a long method to prove it. But we're going to do this exactly the same way we do all of the other questions. So 0.126 grams of vanadium was made up to 50 centimetres cubed with an unknown acid. Unknown means we don't really care. The resulting solution contained VO3 minus ions, and this was yellow. This yellow solution was reduced and a violet solution containing vanadium N plus ions was left. 10 centimetres cubed of the violet solution was oxidised back to VO3 minus by 13.2 centimetres cubed of 0.0225 moles per decimetre cubed aqueous potassium permanganate. So the first thing I'm doing again is just pulling all the numbers out and putting them in one place to make my life easier. So starting off like we do with all of these, working out the moles of the manganate ions in exactly the same way that we've done before. We are not going to start with the equation because we don't know what the charge on the vanadium ion is, or rather we shouldn't. We have to pretend that we don't know what the charge on the vanadium ion is, so we can't start with the equation. We're going to use the equation to prove the charge. So our moles of our manganate are 2.97 times 10 to the minus 4. The moles of the vanadium come from the question. We got given the mass in the question and we can look up the MR from the periodic table. So we know how many moles of vanadium we used. Now we can work out the ratio. Now we can work out the moles in 50 centimetres cubed. You can either do it this way or you can do it the other way around by dividing the moles of vanadium by 5. So we have 1.485 times 10 to the minus 3 moles of manganese reacting with 2.48 times 10 to the minus 3 moles of vanadium. We need to work this out as a ratio. Like empirical formula, divide this by the lowest number, which is 1.485 times 10 to the minus 3. We have 1 mole of manganese reacting with 1.67 moles of vanadium. And if you know your fractions, this is going to be in a 3 to 5 ratio. So we have 3 moles of our manganese is going to react with 5 moles of vanadium. Now we can use this information to construct an equation and then we can work out the charge. So our 3 moles of manganese with 5 moles of vanadium with our unknown oxidation state. From the question, we know that it goes back to VO3 minus ions. And then because the only things we can add in are hydrogen ions, electrons and water to balance this out, that is what we are going to do to balance out this equation. On the right hand side we have 15 oxygens and on the left hand side we have 12 oxygens. So we can add in 3 waters on the left hand side to balance that out. Now we've added in 6 hydrogens on the left hand side, we have to add in 6 hydrogen ions on the right hand side. Now we need to balance our charges. And because this is an overall equation, there aren't going to be any electrons involved in this. Balancing the charges is going to tell us the charge on the vanadium ions. So the total for manganese is 6 plus, the total from vanadium is minus 5, and the total from hydrogen is 6 plus, giving us an overall charge for that side for plus 7. So from manganese we have minus 3, from water we have nothing, and then we have 5 times x, our unknown charge. Now we can turn this into a lovely algebra equation. So we can say that minus 3 plus 5x is equal to plus 7. So 5x is equal to plus 10, which means x must be equal to plus 2. So the charge on the vanadium ion is going to be vanadium 2+, which really conveniently fits in with what we know about the colours. Ouch! This is why in some videos I have unexplained scratches.